Hello and welcome to Chapter 3, Section 3.1. Today we're going to do a short little lecture on properties of linear functions and how we can use these linear functions to create some models in the real world. So today's topics, first we're going to graph linear functions. We're going to go back and revisit that a little bit from before. We're going to revisit that average rate of change equation that we talked about, and we're going to use it in order to identify whether a function is linear or not. Then we're going to find a way to determine whether this function is increasing, decreasing, or constant. And then finally, we're going to do some word problems. I know it's terrible, but it'll be fine. We're going to go step by step. It's going to go slow. We'll be fine. No big deal. We're just going to do two. So the first thing we're going to do, let's revisit a little bit about graphing linear functions. So a linear function is going to be in that form of f of x equals mx plus b or y equals mx plus b. We know from this equation that the slope is m and the y-intercept is b. And its domain is going to be the set of all real numbers. So let's take that to the next level. Let's graph a linear function and figure out what the domain and range of f are. So from this, I can see that my slope, or my m, is going to be -3, and my y-intercept, or my b, is going to be equal to 7. My equation right here says f of x equals -3x plus 7. So remember, y equals mx plus b, f of x equals mx plus b. Okay, we're using that same equation throughout today. So first, let's plot the y-intercept, because we know that that is going to be a point of 0, 7. So we go 0 and come up to 7, and we're going to put a point there. From there, we know that the slope is a -3, and our slope is our rise over our run, so our rise is going to be -3, but because it's negative, so we're actually going to go down 3, so 1, 2, 3 over 1, 1, 2, 3 over 1, 1, 2, 3 over 1. Okay, let's connect those points into a line, and we get something that looks like that. From this, we can actually see that my domain is going to equal my range, and it's going to be all real numbers. So -infinity to infinity on both. Now, if we look at the average rate of change, let's go ahead and put our graph here, much better graph than mine. If we remember, average rate of change is the change in y over the change in x. So as I'm going down, here's my equation, my f of x. I am, between my values, my change is going to be -3, okay? As I continuously go down, it's going to stay -3. Because that rate of change is a constant, that is what makes it a line. Okay, so now let's use that little bit of information that we just had to describe and to figure out whether a function is linear or not. So if we look at what we just said, linear functions have a constant average rate of change, so their slope is a constant number. So the average rate of change for any function, f of x equals mx plus b, is going to be m, which is going to be the slope, which is going to be delta y over delta x. That's the slope. Okay, that's your rate of change. Now, let's take a look at a semi-word problem. Oh, please don't freak out. So we're going to do A and B completely separate. So A is going to use this table on the left, B is going to use the table on the right. So A says a strain of E. coli, known as blah, 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 because we don't care, is placed into a petri dish at 30 degrees Celsius and allowed to grow. The data shown in the table was collected, the population is measured in grams, and the time in hours. So plot the ordered pairs X, Y on your graph and use the average rate of change to determine whether the function is linear. Okay? Remember, we know it's linear because it is the slope does not change, it is constant. Then for B, the data in the right table represents the maximum number of heartbeats that a healthy individual of different ages should have during a 15-second interval of time while exercising. Plot the ordered pairs XY in the Cartesian plane and use the average rate of change to determine whether the function is linear. So for both of these, the main idea is to find the slope of the line, determine whether it's linear by using that average rate of change. Let's pull out A and do A by itself. So first, we're going to compute the average rate of change of the function. So, and if that average rate of change is constant, the function is going to be linear. If the average rate of change is not constant, then the function is not linear. So the first thing that we're going to do is, here's our table just rewritten. And what we're going to do first is plot these points. So we've got like a 0 and a 0.9. So that's probably like here. We've got a 1 and a 1.2. We've got 2 and 0.16. My little points are terrible, but there they go. They're going to go up in like that, okay? Now, in order to determine, it doesn't look like it's linear, but let's make sure by using the average rate of change function. So delta y over delta x. Let's take the first 2 points. So we'll take that one and that one. So we've got 0.09 minus 0.12 divided by 0 minus 1. What that's going to give us is, let's see, 0.09 minus 0.12. It's going to be 0.03 minus over a negative 1. So that average rate of change is 0.03. Now let's look at these last two at the bottom. Okay, so we've got 0.39 minus 0.29 over 5 minus 4. So it's going to be 1, and it's going to be 0.1. Okay, those are not equal. Because those are not equal, this is definitely not a straight line. So this is part B. We're just going to go ahead and plot these points. So if I say 250, I know my graph is not actually made for something like this, but that's okay. So 347, and let's see, 640. So I've got something that kind of looks like that. It does look like it's linear, but we can actually go ahead and do that the average rate of change to verify. So let's pick out the first 2 points. So we've got 50 minus 47.5 over 20 minus 30. That'd be 2.5 over 10. Do the same thing for these last two. 40 minus 37.5 over 70 minus 60. And this is negative actually, right? Equals 10 minus 2.5. Those are equal. So I can look at the graph and say it looks equal, but here I have proven that it is equal because I have proven that the slope is the same and constant all the way between all of those points. Now, a cool thing we can do is that we can actually use that slope to determine whether a function is increasing, decreasing, or constant. Now, we talked about that concept in general a couple lectures ago, but let's go ahead and look at a theorem real quickly about functions and whether they're increasing, decreasing, or constant. So a linear function, now we're talking linear now, and we're saying it is going to be increasing as long as your slope m is a positive number. Now, on the flip side of that, if your slope is a negative number, then it is going to be decreasing. So positive slope, climbing up the hill, you're increasing. Negative slope, you're falling down the hill, it is decreasing. And the one caveat that we have is that if your slope happens to be equal to 0, then that is where you're going to be constant. So your function is just going to be a constant number. Let's look at a few different examples and determine whether these functions are increasing, decreasing, or constant. So for A, we've got f of x equals 5x plus 2. So my slope equals 5, okay? Y equals mx plus b. We're looking for these m's, okay? That's, in this case, that is all we care about. If we're looking about increasing, decreasing, constant, we only care about the m. We don't care about any of those other numbers. This happens to be a positive number. Positive. So we are increasing. Okay, number B? Yeah, that works better. G of x equals negative 2x plus 8. My m is equal to negative 2. Remember, that's all I care about. That is going to be a negative number, and therefore it is decreasing. For C here, my m is 3/4. I don't care that it's a fraction. All I really care is that it's positive. And therefore it's increasing. Okay. Now, if I look at part D here, this is actually the same as saying 0x plus 7. Okay, so my m here is actually 0. Because it is equal to 0, it is going to be a constant in that section. I forgot the s. There we go. It's constant. So when you're looking at whether it's increasing, decreasing, or constant, remember, just look at the slope. You don't care about anything else. Just ignore the other numbers. All you need to know is the slope. Now we come to the fun part. We're going to do 2 different word problems, and we're not going to panic. And I'm not going to panic with you, I promise. So the first one we're going to look at is, we're going to have to pull this apart. Okay, so what we want to know is the average rate of change. Okay, we can use the variables given within a word problem to create an equation of a line, okay, as long as we know what's going on. So what this is saying is if the average rate of change of a function is a constant m, a linear function f can be used to model the relationship between the 2 variables. We've already shown that. We've already proved that. So now let's take that, though, and put it into what they're calling a model, or what most people call a word problem. So for example, we're going to have a straight line depreciation. So what I'm saying is book value is a value of an asset that a company uses to create a balance sheet. Some companies depreciate assets using straight line depreciation so that the value of the asset declines a fixed amount each year. Okay, the amount of the decline depends on the useful life that the company assigns to the asset. So we're going to use vehicles as an example for this. So suppose a company just bought new cars for its sales force. It paid $31,500 per car. Apparently really nice cars, nicer than my car. Anyway, the company is going to say that it is going to lose value using a straight line method over 7 years, okay? So it is going to depreciate from $31,000 to be worth $0 in 7 years. So the depreciation is it's going to lose $4,500 every year. Okay, we're going to do several different things. And as always, we're going to pull out every single piece, each on its own, so no panic. Write a linear function that expresses the book value v of each car as a function of its age x in years. We're going to graph that linear function. We're going to figure out what the book value of the vehicle is going to be after 3 years. We're going to interpret what the slope actually means. And then we're going to look at when will the book value of this vehicle be equal to $9,000. And a hint on that is that we're going to set the equation equal to 9,000. So first things first, let's go to part A, write a linear function that is going to express the book value v of each car as a function of its age. So we want to do a value with respect to age, okay? So we're going to say v is the value and x is age. X is going to be the number of years, okay? Now, we know v of 0, which is the original value, is that crazy $31,500, okay? Now, an f of 0 is the y-intercept, so that is going to be your b in your equation. Remember, we want to do y equals mx plus b. B is going to be your intercept, okay? So we're going to say the car loses $4,500 per year, okay? So it's going to change by negative $4,500 per year. So that's going to be our slope. We're going to slide down the slope $4,500 per year. So we've got our y equals mx plus we have our b. So now we've got our linear equation, okay? Remember, x is years, so at year 0, we paid full price, okay? And we are sliding down the slope. We're losing money every year. We're losing $4,500. So that's our slope. Now, graph the linear equation. Now, this one is terribly, terribly not anything close to what we need. Anyway, here, let's say this says 31,500 up here, and let's say this is 7 years, okay? What we're going to do is it's going to do that. It's going to be a straight line. Okay. Okay, here's a better look at that, and I can write the equation a little bit better here. So our m is minus 4,500 times the years plus 31,500. That's our equation, and that is what the graph is going to look like. Now, for part C, C says what is the book value of the car after 3 years, and then we want to interpret the slope. So our equation, again, remember, v of x is equal to minus 4,500 x plus 31,500. Okay, that's our equation from before, from A. We want to know when x equals 3 years. Okay, so the value is going to be equal to minus 4,500 times 3 plus 31,500. We put that in our calculator. Our value is going to be $18,000. 3 years. Okay, all we do is plug that in. So interpret the slope. So the slope is the minus 4,500, which is our m. So basically what we're saying is that the value is decreasing by $4,500 each year. Okay, it's decreasing because it's negative, and it is the amount. Okay, remember we just said increasing, decreasing, and constant. Decreasing is negative, you're falling down the hill, so you're losing that much amount of money. So when will the book value of each car be $9,000? So here, let's write our equation that we already know. There we go. Let's set that equal to 9,000. Okay. Subtract 31 from each side. And I get, just changing sides here, equals negative 22,500. Okay. Oops, I've got a 0. Divide by that. My x is going to be equal to 5. So, at year 5, the value is $9,000. Okay, so we've taken that equation, we were able to figure out what the value is after a certain amount of years, and we've also then determined how many years it'll take to reach a specific value. Again, we're taking the information that we have and we're just creating a function using our straight line. Let's do one last example and then you can let your brain rest. So we're going to talk about supply and demand. So the quantity supplied of a good is the amount of a product that a company is willing to make available for sale at a given price. A quantity demand is the product that consumers are willing to purchase at a given price. So what we want to know is here we're actually given two equations. Our supply is equal to 40p minus 200, and our demand is minus 20p plus 1,000. P is going to be the price in dollars, okay? So we're giving our supply and our demand in terms of dollars. Now, the first thing we're going to look at is the equilibrium price. So the equilibrium price is the price at which the quantity supplied equals your quantity demanded. Okay, so we're going to have to find that equilibrium quantity, the amount demanded or supplied at the equilibrium price. Another thing we're going to do, we're going to determine the prices for which the quantity supplied is greater than the quantity demanded. So we're going to solve for that inequality. And then we're going to graph the two. We're going to graph supply and graph demand. And from that, we're going to find the equilibrium point and we'll label it. So let's get started on part A. So the equilibrium, by definition, is where S of P equals D of P. So let's set those equal together. 40p minus 200 equals minus 20p plus 1,000. Okay, now let's solve for P. So if I add 200 and add 20p, I get 60p equals 1,200. I get my P is equal to 20. Now remember, P is a price, so it's going to be $20. Okay, so the equilibrium price is $20. Now the question is actually saying what is the quantity? So we take that and put that back into one of these equations. So my supply quantity is going to be equal to 40 times 20, minus 200. So my quantity at my price of 20 is going to be 800 minus 200, or 600. So my equilibrium price is $20, and the amount demanded and supplied, because remember, supply equals demand at this equilibrium, is going to be 600 gadgets, widgets, or whatever it is we're selling. Now let's move on to B. So here they actually give us the inequality. So for 40p minus 200, we want to know where that's greater than minus 20p plus 1,000. Again, let's add 200, add 20. Nothing that we've done there has flipped our sign, so we get 60p greater than 1,200. P greater than $20. Okay, so if the company is going to charge more than $20, then they're going to have that where the quantity supply is going to be more than their demand. So their supply is going to be more than their demand. So in this case, your company is going to have excess in inventory, which makes sense because you just said if the equilibrium was 20, it's either going to be less than 20 or greater than 20. That makes sense. Last but not least, let's go ahead and do a graph of this. I'm going to be honest. I'm just going to go ahead and get the final picture because my pictures are terrible. Okay, I'm just going to put that graph right over it because my graphing skills not very good. But you can see here from S that your M is going to be 40. Okay. Remember, Y equals MX plus B. And your intercept is going to be at negative 200. For D, your slope is going to be minus 20. And your intercept is going to be at 1,000. So here you can see your supply is going to be increasing because you have a positive M. And your demand is going to be a negative M, so you're decreasing. Okay. So here we've got our D is decreasing and our S is increasing. Now that equilibrium point that we calculated is where those two graphs intersect. Okay, but you would plot those two lines just like you would anything else. You've got a minus 200 with a slope of 40, and then you have a plus 1,000 with a slope of minus 20. And then that's going to give you the shape of your graph. Hopefully you've learned something good in this introduction to chapter 3. As always, if you have any questions, ask your professors, and I will see you next time.